Welcome to the second part of the three-phase balance fault video series. As I promised in the first part, I will demonstrate to you how we are going to analyze a balanced three-phase fault that is happening on this network. And in this part of the video, we are going to look into this. And let's begin by assuming that there is a three-phase balance fault striking bus 3. So if there is a balanced three-phase fault striking bus 3, we can represent the fault as an impedance. And this is the value of the fault that is happening at bus 3 right now. And there's one thing that you need to notice is there is a switch over here. The switch is used to represent the connections of this fault impedance to bus 3. When the switch is opened, that is when a fault hasn't occurred yet. And when the switch is closed and the impedance is connected, that is when the fault has set in. So the usage of this impedance is in line with what we mentioned in the first part, that the modeling of the fault is performed by introducing impedance at the place where the fault has occurred, such as like this. There are more things that we need to consider in such a network and the changes that is introduced by the fault impedance over here. First of all, when the fault impedance is connected to bus 3, we are essentially saying that there's a balanced three-phase fault at bus 3. And don't forget that the balanced three-phase fault is a short circuit fault. So when you have a short circuit, then you have a large inrush current flowing into the source of the fault. So that for this reason, we are going to consider that the fault current is flowing from bus 3 to the ground, and we call it I3F. So if we have a fault current, then we should have the voltage value of the fault as well. And we are going to call it as VTH over here. So the reason that we call it VTH, or the Thevenin voltage, is because later on we are going to perform Thevenin analysis. And this is due to the fact that the remaining sections of the network will remain unchanged, and only this section of the network is a variable. And that is in line with the strategy that the Thevenin theorem is giving to us. The directions of the voltage source is arranged in such a manner because we are assuming or considering that the fault current is flowing from bus 3 to the ground. To understand this manner of arranging our voltage source, we can refer to this simple analogy. So when we define that the current is flowing in this direction, then the positive is at the top like this. And when we switch the directions of the current, then we also have to switch the polarity of the voltage source. And this arrangement is similar to this one. Another thing to take note is that the voltage of this fault, which is what we call the VTH, is actually equals to the initial voltage at bus 3, V30. The reason is because the moment before and immediately after the switch is closed, that is, the moment before and immediately after the fault happened, the voltage at bus 3 remains the same. And the voltage at bus 3 before and immediately after the fault happened is equals to the initial voltage of the bus 3. So the initial voltage of bus 3 is 1 per unit. And the reason for this value is because we established earlier, as you can see over here, we have established earlier in this network that this network is operating under the no-load condition, so there is no voltage drop along the lines. And the generators are also operating at their rated voltage. Therefore, when we convert them to per unit, it will have the value of 1 per unit. And if there is no voltage drop along the lines of the network, then whatever voltage you are seeing here is transferred directly to the bus, and this is transferred directly to bus 3. And for this, due to this, the voltage at bus 3 is equal to 1 per unit as well. One more thing to notice is observe how the generators have now changed into ground, meaning that we have removed our generator, or we have short-circuited our generator by connecting it directly to the ground. And also, our transformer has become short-circuited. So this has to do with the Thevenin theorem, which says that when we apply the Thevenin theory and when we want to determine the Thevenin resistance at the point of our observation, which is at bus 3. So when we are looking into the network from bus 3, because this is where the fault happens, and we want to simplify this portion of the network, we need to determine the RTH, which is the Thevenin resistance. So when we are determining the Thevenin resistance, the first thing we need to do is we need to switch off all the active sources, and that include our generator and transformer. So transformer becomes short-circuited and the generator becomes short-circuit because generator is a voltage source and transformer is also a voltage source. So voltage source, when you switch them off, they become short-circuit. And let's go back a bit. So when these two become short-circuit and they connect together directly, so they form a series circuit. And when they form a series circuit, the impedance of this branch can be summed up together. So this is the same as what is happening over here. And this explains the values of these two. Okay. So with the establishment of this network, and you understand what is going on over here, we are now ready to perform Thevenin theory. So this slide is purely on Thevenin theory. So if you have forgotten, so I recommend that you actually go and revise on the Thevenin theorem at your own pace. So the first thing to do is we need to look straight into this network from the perspective of the fault. Okay, there's a difference, yeah, where you look from here or you look from the top down. There's a difference, which I will explain later. So another way of looking at this is given by this network. So because this branch and this branch are connected to the ground, so they are sharing the same node. So I can connect them together like this. So the rest, I think is quite clear how 0.2J and 0.4J is connected in between by 0.8J. So I think it's quite clear. And same as this as well. So just now I mentioned that if you want to simplify this, you can simplify them by looking from the top down or down into the network from the source of the fault. If you're looking from the top down, then these two are in series, which is further in parallel with this, and then the results of this tree can be simplified into the Y connection. But that is not the case, okay, if you're looking from the bottom up. If you look from the bottom up, we have to start from this portion and work our way up. So this delta has to be converted into the Y first, because this is a delta connection and we can't do anything with it. We cannot simplify this portion. The only way we can simplify further is by converting them into the Y network, such as like this. So when you have converted them to Y network, such as like this, then the rest is quite clear. Because these two, they are in series. These two, they are also in series. So the result of the two branch later on, they are in parallel, and you can convert them and combine, become this value. So this value and this value can be further combined to form the final value of 0.34J over here. So this is what we call the Thevenin resistance. We call it Z33, such as like this. So now our objective is to determine the fault current. Don't forget about that. We can redraw this type of arrangement into this portion, into this circuit, which is clearer in my opinion. So how do I do that? Is simply by tracing the flow of the current and also the polarity of the components. So first, let's start from the from bus 3 over here and walk down. Yeah. So at bus 3, as I walk down, I meet negative VTH. So I just draw negative VTH accordingly. And then I meet 0.16J, so I draw accordingly. So as you enter the ground is also here. You enter Z33, which is 0.34J. So this is how you redraw these portions of this network into this series circuit. So by performing the analysis of this circuit, we determine that I3F is equals to negative 2J. Okay, negative 2J. So one thing to take note is that the divisions of imaginary J will give you negative j. Yeah, so don't forget about that. So that's how you get the negative j from the divisions of two positive values. Okay. So just now we work our way from the bigger network down into the smaller one. And now we want to work our way backward instead, because we want to find what is the fault current in each of the branch, and also what is the voltage in each of the bus after the fault happens. So to do that, we need to break down this current value instead. Okay, just now we combine them and then we find the current. Now we have the current. We want to break the current down so that we can find what is the current flowing and also the voltage of the bus. So to do that, you just work your way backward. So just now, this is the result of the series summations. So you break them apart. So because they are in series, the fault current remains the same over here, which is negative 2J. Oh, by the way, this is negative 2J because these two components are in series. So if this is negative 2J, so this is negative 2J as well. So, so here you break it down to 2, and these two are in series, and that is why the current remains negative 2J. But from here, 0.24, when we want to break down the two branches that are in parallel, we cannot do that anymore because negative 2J is the summation of these two parallel branches. Okay. So to do that, we simply perform the current divider rule. So to find the current flowing in this branch, we take the opposite impedance, 0.6J, divided by the total impedance, 0.6 plus 0.4, such as like this, multiply with negative 2J, and then you get the current flowing in this branch as negative 1.2J. Performing the same, you will obtain negative 0.8J over here. Okay. So now we are ready with the current flowing in this branch we know, and the current flowing in this branch that we know, and also the current flowing in this branch that we know. Now we are ready to determine what is the change or the delta of the voltage at bus 1, 2, and 3. By the way, there's a slight mistake over here. This should be negative 2J, yeah? Negative 2J. Okay, they just a mistake in my writing. It will not affect the calculation. The calculation remains valid. Okay, so just like I mentioned, with the knowledge of the current or the fault current flowing, we are now ready to determine the change in the voltage value of bus 1, 2, and 3. And why do I say change or delta, such as like this over here? Because before fault occur, there is no current flowing. Okay, remember that the voltage is operating under the no-load condition. So before fault happening, there is no current flowing in the branch. But when fault happen, then we have the introductions of the fault current. So the fault current represents the delta of the current flowing in the branch, or in other words, the change of the current flowing in the branch. So if I have the delta of the current flowing in the branch, multiply with the impedance, I will get also the delta of the voltage of the bus. As simple as that. If we look at this bus number 1, which is connected to ground, we do know that the higher potential is over here, and this is the lower potential. So if I want to determine the voltage value of bus 1, I simply take the voltage drop along the impedance. However, remember that this is the delta I flowing, which is the IF of this branch. The IF is the I fault of this branch. So the fault current of this branch flowing from bus 1 to ground, multiply with the impedance over here, that will give me the delta of the voltage of this bus. Okay, I repeat, why delta? Because the fault current flowing in this branch also represent the delta of the current flowing in this branch. Because compared to the previous scenario, before fault occur, there is no current flowing in this branch at all. So negative 1.2J is defined in these directions. So then therefore 1.2J is in the opposite directions from bus 1 to ground. And that is how we managed to obtain this equation. 1.2J multiply 0.2J, we get negative 0.24 per unit for delta V1. And the same we perform over here in bus 2. applying the same logic, we get negative 0.32. So the same logic is applying at bus 3 as well. To get the change of the voltage at bus 3, I simply calculate the voltage drop along the branch. So that will be, walking down from bus 3 to ground, that will be negative VTH plus I3F multiplied 0.163, which is given over here. And then you get negative 0.68. So the negative value makes sense because when you have fault happening or short circuit, you will have an inrush of current flowing into the ground, and that will cause a voltage dip in your buses. This phenomenon is similar like having a blackout at your house. So the reason you have blackout is because the voltage in your house has dropped from 240 volt to 0 volt due to short circuit. So the same applies here. You have a negative change of voltage. It makes sense because you are having now a three-phase balance fault at bus 3. The same mistake is over here as well. Hold on. There's a mistake over here as well. This should be negative 2J. Okay, sorry about that. It doesn't affect the calculations. This is actually a repetition of this. These two are the same. So with the understanding of the change of the voltage in bus 1, bus 2, and bus 3, now we are able to determine what is the voltage value of bus 1, bus 2, and bus 3 after fault occur, simply by taking the voltage at each of the bus before fault occur plus the change of the voltage in each of these respective bus, as like this. So I simply take the V1 before fault occur plus the delta, then I will get the final V of bus 1 after fault occur. And I repeat for all the 3 buses. So with the knowledge of the bus 1 voltage, bus 2, and bus 3 voltage after fault occur, I can simply and easily determine what is the final current flowing in between them by taking the difference of voltage between the 2 buses and divide by the impedance between them, such as like this. And I repeat for all the branch. And this is what I get. Yeah, this is the final current that is flowing in the branch after fault happening, which will result into a negative value. The negative value of the current that we see in each of the branch makes sense as well, and the explanation is similar to how the voltage in the buses actually drop when we have a fault current. So if the voltage in the bus drop, then you should expect a drop in the current flowing in the branch as well. So initially they were 0. So if they drop further, then you have a negative value. So all right, so this is the end of the second part of the 3-phase balance fault calculations. In the third part of the video series, I will perform 2 more examples so that you are more familiar with the calculations of the 3-phase balance fault, and that also serve as a revision for your Thevenin theorem. Thank you for listening, and see you in the next part of the video.